Good afternoon. Hello. Good afternoon. Hello. Chaitanya. Sauro Mahapatra. Tamreen Fatima. Kasturi. Sahana. Untipalli Ashmita.
Good evening, sir.
Good evening. Good evening. Asta. Maji Shruti. Good evening. Because hardly there are 7 students, of which I just called up 3 or 4. There was no response. It's already 4:15.
Good evening,
Maji
sir.
Shruti. Good evening. Good evening.
Good evening, sir.
Good evening. Let's just wait for 1 or 2 minutes. It is very poor as of now. Okay. That's already at least 10 students are there. Welcoming to context section 2. Once again, as I told you in the last session, just a few slides are left to be covered from the last session about solving a linear system of equations. And then we will proceed to session 2's contents about vector space, linear independence and dependence of vectors. Yes. And expansion of 2 by 2, 3 by 3 determinants, using determinants how to solve linear system of equations. Okay, so all these things will take place in this session. Okay, first I will take it up this. Let me see. No. Vectors. So already in the last session, you were exposed to what a vector is. Whenever you have a row matrix or a column matrix, it will be referred to as a row vector or a column vector. Usually matrices are represented by uppercase alphabets, while the row vector or column vector can also be denoted by usually lowercase alphabets, but with boldness. Because normally in the last session itself, I gave you the representation to be given for any vector to be having the small letter overhead, a bar or an arrow mark to mean the direction. As you all know what a vector is. So in the absence of putting any bar or arrow mark, at least the vector can be boldened. But here, of course, you have to take it as there is a bold A. A vector is a matrix that has only one row or one column. So a row matrix or a column matrix can also be referred to a vector. So here, vector A, it is to be construed as vector A with some kind of boldness as if. So you have a row vector whose components are A1, A2, etc., AN. Don't put any commas. You have to have it. Remember that it is a matrix arrangement, row matrix like. If the matrix has only one row, we call the matrix row vector. Similarly, column. If the matrix has only one column, we call it as a column vector. In both the cases, we call its entries as components and denote the vectors by lowercase alphabets, of course, with the bold faces A, B, C, etc. Look at this. You might have seen an ordered n tuple. What is meant by an ordered n tuple? You might have heard, you might have done in analytical geometry or in geometry by plotting a point having two coordinates, normally on a two-dimensional plane or a graph sheet, x comma y. X, so suppose you have from the origin, you have OX and OY, two mutually perpendicular axes. So at a distance of OA, you draw a point, an ordinate perpendicular to, parallel to y-axis at a distance of x, OA equal to x. And then that OB is along the y-axis at a distance of y. So along the x-axis, you have OA equal to x. Along the y-axis, you have OB equal to y. So that you plot a point x comma y, which is called an ordered pair. Of course, if you generalize it, x1, x2, or x1, x2, x3, x1, x2, etc., x. And here you have the commas. Remember, this is a point whose coordinates are separated by a comma and then enclosed within ordinary brackets. Okay, you have to have a distinction between the point on the plane or in space and so on. So an ordered n tuple means you have n coordinates x1, x2, etc., xn separated by commas and enclosed within ordinary brackets, which means a point, a sequence of n real numbers. We are only taking the coordinates to be real numbers. So you have Rn space. Here Rn means, see, don't be under the impression it is R into n. So but you read it as Rn means here R super n otherwise. B means you have R cross etc. cross R. Isn't it? So Rn space the set of all ordered n tuples. That means each point is an ordered n tuple. Suppose you have the point capital X1, then whose coordinates are x1, x2, etc., xn, capital X, then capital Y, y1, y2, extra yn. So that each point in Rn space will be set of all ordered n tuples. So what practically you have seen so far might be a point on the line. Then you have point on a point on the point on a two-dimensional plane, and then you have a point in space having three coordinates, and so on. So for example, if you put n equal to 1, you say R1 space. That is, we don't normally say R1 space, which is nothing but set of all real numbers. That is, R1 space means geometrically the x-axis. So on the x-axis, you are having set of all real numbers from minus infinity to plus infinity. It is one-dimensional. N equal to 2, R2 space. So it has got points. Each point is an ordered pair. X1, x2, set of all ordered pair of real numbers of the form x1, x2. R power 2, R super 2 space means, R2 space means geometrically the xy plane. That is, you have OX and OY, which are mutually perpendicular. In other words, it's two-dimensional. Isn't it? Then n equal to 3, R3 space, set of all ordered triple of real numbers. X1, X2, X3. Any point in space will have, you know very well. If you have a point in space, you write x comma y comma z or x1, x2, x3 with reference to OX, OY, and OZ. Isn't it? You have the plane here. Supposing this is y-axis and this is x-axis, then you can draw an axis perpendicular to this OX and OY from the at the point O, namely OZ, which are mutually perpendicular axes. Three mutually perpendicular axes. So that you have the point with reference to x-axis, OX equal to A, and suppose x1 and OB equal to x2, OB equal to x2, and OC equal to x3, which are all measurements along OX, OY, OZ axis. Is it right? So you have a point having three coordinates, which you call it as ordered triple. That is triple. N tuple, like this is three tuple or triple. Okay. Then n equal to 4, R4 space, set of all ordered quadruple. It's quadruple. That means there are four coordinates, x1, x2, x3, x4. Okay. So these are all. So we don't practically go for R5, alpha. Of course, you can write if you have ordered five tuple. So you have 5 tuple, 6 tuple, etc. In general, n tuple. An n tuple can be viewed as a point in Rn. So when you regard or when you view x1, x2 as a point in R2, because with reference to two axes, R2 space, it's a point. So naturally, n tuple x1, x2, xn can be viewed as a point in Rn space with the x-axis as its coordinates. And n tuple x1, x2, xn can be viewed as a vector. So with reference to geometry, it is a point in Rn space with x to be its coordinates. Now, the same can be viewed as a vector x, bold x, equal to x1, x2, etc., xn in Rn with x's as its components. So when you have a row matrix, you just write them without separating them as commas. You don't need to put commas here. You just write them as components, which is nothing but actually a row matrix or a vector. So in that sense, when it can be viewed, then the entries are called components. For a point in the space, they are viewed as a coordinates. So that is how you differentiate between a point in the space and the vector. Suppose you have x1, x2, x3. It's an ordered triple, or it is a three tuple, isn't it? A point in R3. Whereas the same can be regarded as x is equal to x1, x2, x3, a vector, where x1, x2, x3 are its components. So you just look at. So how do we distinguish between a point and a vector? So when suppose this is O, you know very well. O. This is a point on the x-axis. This is your x-axis, or you say y-x. Similarly, this is y, and this is the point P on the y-axis. And you are taking the measurement OA is equal to x1. And this OB is equal to x2. If it is y, you will write x comma y. So it's all just notations. Okay. So now what's happening? Therefore, corresponding to, so you draw a perpendicular to this point A on the x-axis, where foot of the perpendicular is at a distance of x1 from the origin, is your x1. And similarly, and this distance OB being x2, and this is the point, this is the coordinate x2, so that there is a point. Normally we write it as P. Is it right? Point. So remember, this is not 1, this is 2. Okay. So here is a point on the plane. So this is a point having 2 coordinates. So the same can be viewed as a vector. You have x1, x2. You have here O is having coordinates 0, 0. Now you put the arrow mark. So suppose that you can mention it as same P. And this is of course O. Now this OP becomes, with the direction towards P, a vector, isn't it? And you know, so a vector on the plane is expressed as a directed line segment whose initial point is the origin and the terminal point is the point x1, x2. So when you have a line joining 2 points being a scalar, and when you mention a direction, this is being from O to P, so it becomes a vector. Now, linear dependence and independence of vectors. These are very two important concepts of your vector characteristic. Given any set M of M vectors, you can write A1, A2, etc. AM. This author has taken specific notation, 1 within brackets, etc. M within brackets, or you can always simply write A suffix 1, comma, A suffix 2, etc. A suffix M, set of M vectors. That's why you see it boldface, A, with the same number of components, each one. A linear combination of these vectors is an expression of the form. So you can have vectors themselves can be summed up using scalars as a combination. So such a combination is called a linear combination of these vectors. What is the form? C1A1 plus C2A2 plus etc. plus CMAM. Remember, each one of the vectors is again having its own components. Maybe a pair or a 3 tuple or a 4 tuple or etc. n tuple. Okay. Here each one is a vector. So there are m vectors, and these vectors can form a linear combination, so that you just remember the linear combination. So you have each of these vectors multiplied by scalars, where C1, C2, etc. CMA are scalars. Now, finding a linear combination given V1 a vector 1, 2, 3, V2 vector 0, 1, 2. In fact, it's a row matrix, isn't it? Okay. V3 minus 1, 0, 1. W is equal to prove that given 3 vectors, remember, like you were, as you had just in the theory, A1, A2, etc. AM, here are V1, V2, V3. And each one of them is a vector having finite number of components. In practice, you will have about 2 components, 3 components, at times 4 components at the most. So here are vectors. Each one should have the same number of components. That's very important. So there are 3 components. Each one of them has. So prove that there are 2 questions. W equal to 1, 1, 1. W is yet another vector having same number of components. Is a linear combination of these 3 vectors. We just have seen that given any set of vectors, finite number of course, you can have linear combination of those vectors using scalars in the form of C1A1 plus C2A2 extra plus Cnam. Here are vectors V1, V2, V3. Well, each one is having three components. Okay. And you are given a vector W. The question is prove that W111 is a linear combination of given V1, V2, V3. How do we do it? Now, let us suppose it's given prove that. Okay. So let us suppose W can be written as a linear combination of V1, V2, V3. So what is the format? W is equal to C1 V1 plus C2 V2 plus C3 V3. Remember, the vectors are having bold faces. Very bold. So what is W111? C1 into 1, 2, 3, C2 0, 1, 2, C3 minus 1, 0, 1. Now, how do you do it now? So this will become a vector. Isn't that? You know scalar multiplication of each of the vectors, components, and their addition. So we'll form a vector. So how will it form? C1 into 1 plus C2 into 0 plus C3 into minus 1 will form one component. C1 into 1 from the first vector, C2 into 0, second vector, C3 into minus 1. So you have C1 minus C3 a component, comma, 2C1 plus 1C2 plus 0 to C3. So you just have only C2C1 plus C2, comma, and third C1 into 3, that is 3C1 plus 2C2 plus, just look at 3C1 plus 2C2 plus 1C3. So that forms the third component. Previously you had 0C3, that is 0 plus 1C2 plus 2C1, second component, and first component minus C3, this is 0 plus C1. So C1 minus C3, comma, 2C1 plus C2, comma, 3C1 plus 3C2, 2C2 plus C3, third component. So this becomes a vector enclosed within brackets. And this is being equal to 1, 1, 1. So what is the meaning? Two vectors are equal means the corresponding entries are components are equal. So C1 minus C3 is 1. 2C1 plus C2 is 1. 3C1 plus 2C2 plus C3 is also 1. So now we can solve. You know how to solve by taking any two equations at a time. Cancel, eliminate any one of them, and then sometimes it automatically gives you the other values, or sometimes you have to take another pair of equations again, eliminate the same, because now you have three unknowns, three equations. C1, C2, C3 are three unknowns, and there are three equations you know how to solve by elimination method, isn't it? And therefore, of course, here they have taken one different idea that it's also easy to understand that C1 is written as 1 plus T, actually 1 plus C3. And here C2 is equal to 1 minus 2C1. 1 minus 2C1. So 1 minus 2T. Here C3. So they have taken initially any one of them to be a substitution. So you can put values for T then later on. Instead, you can straight away go for solving for C1 and C3. So here they have taken an arbitrary value. So supposing C3 is equal to T. So C1 will be 1 plus T. And C2 will be 1 minus 2C1. Sorry, C2 will be 1 minus 2C1. 1 minus 2C1. And C1 is already 1 plus T. So minus 2 into 1 plus T. So you have minus 1 minus 2T. And then C3. So from the third equation, you can check. You can check that the 3C1 plus 2C2 plus C3 is 1 whenever you have these three values. So what does W now mean? Having found the C1 equal to 1 plus T, C2 is minus 1 minus 2T, C3 equal to T. So what is W? W is originally C1 V1 plus C2 V2 plus C3 V3. So it is now C1 into V1. 2V. So what is C1 now? Supposing T equal to 1. You can give arbitrary values for T starting from 1. Okay. To be on the safer side. So C1 is 1 plus 1, 2. So 2V1. C2 is minus 1 minus 2 minus 3 minus 3 V2 plus C3 V3. C3 is T equal to 1. So you have W equal to 2V1 minus 3V2 plus V3. So you are able to express W as a linear combination of the vectors V1, V2, V3 using constants C1, C2, C3, where C1 is 2, C2 is minus 3, C3 equal to 1 if T equal to 1. Suppose T equal to 2. So you can generate as many such linear combinations as possible. That's why it is given here. So W is equal to, then T equal to 2, you have W is equal to, so you can generate like that. Now, subdivision B. What is the question? Prove that W is equal to 1 minus 2, 2 is not a linear combination of V1, V2, V3. Why it is so? Let's see now. Of course, we can do by other method also. As we have done in the previous one, the same one you can do. Here's one more method can also be adopted. That is, you can go for augmented matrix. What is here augmented? Here, what is augmented for you got here? Just see that what are 1, 0 minus 1? 1, 0 minus 1. This one, you are taking column because you are taking each component to form the column. First element of V1, first element of V2, first element of V3 forms the first column. Okay. So 1, 0, minus 1. Then, okay, you can take it as a row itself. Yeah. Since we are taking it in the linear form as it is, so you can take it as a row also. 1, 0, minus 1, the first components of V1, V2, V3, isn't it? Because C1, V1, C2, V2, C3, V3. So we are taking the first components to form the first row. Then 2, 1, 0. 2, second component, second component, second component. Similarly, third, 3, 2, 1. So the first, second, third components of the three vectors are taking places of first row, second row, third row. If it is taken in the matrix. What is being augmented here? Now, W. What is W? 1 minus 2, 2. So that is on the other side, isn't it? That is being equated. So that can be taken as a column matrix, that is column vector. So you have an augmented matrix. This is matrix of coefficients of vectors V1, V2, V3, and this is column vector of your W. So using row operations, you can find out this one, you know very well. Once again, I take you to recap, as I said in the first session, to have using elementary row operations. See, it is not mandatory, it is not necessary that you should do only by this one. You can do as well by the same kind of method. This way, I think you may find it easy because you are just comparing, you are making a system of linear equations in three unknowns and you can solve them. Okay, so that is one method. Equivalently, you can go for augmented matrix like this, and you can go for reducing it to echelon form. So when you are reducing it, what's happening? You are keeping row 1 fixed. 1, 0, minus 1, 1. And what's happening? This should become 0. So 2 minus 2 into 1. That is R2 is R2 minus 2R1. That is 2 minus 2 into 1. 2 minus 2, 0. 1 minus 2 into 0. It is 1 only. Minus 2 minus 2 into 1. So minus 4. Okay. Now this is not the immediate next step. It is, so one more step has been skipped and final value is given. I will just show you what is the other step you can do. You have to So what will you do next? You have to make this third row first column element to be 0, isn't it? Fixing same R1 fixed. You have to do two operations. One of R2 on keeping R1 fixed. Another one is on R3 keeping one R1 fixed. So what will you do now? Next operation, R3 is R3 minus 3 times R1. So 3 minus 3 into 1, 0. You will get 2 minus 0, 3 into 0, you will get 2. And 1 minus 3 into minus 1, you will get 4. So you will get in the one more operation simultaneously operating on R3 in on R1, you have 0, 2, 4. Here you will get 2 minus 3 into 1. So it is minus 1, 2 minus 3 minus 1. So that is one step that is skipped here. So what is the next step then? Keeping that R2 fixed now, is it right? Keeping R1, R2 fixed. Now you will have to do one more operation of this, what I have written now, 0, 2, 4, minus 1. Isn't that? That is, you have here one more third row, you will have 0, 2, 4, minus 1. 0, 2, 4. You had this as R3. So what is the new R3 now? R3, you must get here also 0. So here you are having 2, isn't it? So here, what you are having here? 0, 1, 2. R2 is fixed. This is the letter R3 you are having. So this you must get 0 here. So what we'll do here? 2 minus 2 into 1. That is your latest R3 is R3 minus 2 R2. So this is your R3. So your latest R3 will be R3 minus 2 into 2. That is, here you had 2. So this is your R3. Isn't that? So 0 already there. This is 2 minus 2 into 1. So you have 2 minus 2, 0. Next is 4 minus 2 into 2. Isn't that? 4 minus 4, 0. And next is minus 1 minus 2 into minus 4. That is minus 1 plus 8, 7. So you had finally 0, 0, 0, 7. Now, the system has no solution since the third row means, so you just look at, if you just look at this, what does it mean actually? This is 0 into C1 plus 0 into C2 plus 0 into C3. Whereas on the right hand side, you are having 7. Isn't it? It is not equal. So the system has no solution since the third row means 0 into C1 plus 0 into C2 plus 0 into C3 equal to 7, which is meaningless, isn't it? And the way it cannot be. Therefore, W cannot be expressed as C1 V1 plus C2 V2 plus C3 V3. So we just had seen one problem of proving a vector given to be a linear combination of three given vectors, whereas giving different components for the same three vectors of a new vector W that cannot be expressed as a linear combination of given three vectors. So both we have seen. Linear independence. Supposing you have a linear combination equal to 0. There are two possibilities, which is possible only when all the scalars are equal to 0. Each scalar must be necessarily equal to 0. Or not all scalars are 0. These are the two possibilities. So that the sum of all these terms must be equal to 0 is possible. So in the case of all the scalars are equal to 0 is giving rise to the definition that the vectors are linearly independent. If not all CIs are 0, not all scalars are 0, Not all scalars are. Even if there is one scalar that is non-zero, but still the summation is zero, then we can say the vectors are linearly dependent. Okay. If S, capital S, is set of all vectors, V1, V2, extra, say VR, is a non-empty set of vectors in a vector space V, then the vector equation K1, V1 plus K2, V2, etc. plus KR, VR equal to 0 has at least one solution. At least one solution. What is the trivial solution? See, normally in any equation, when we solve, we are always interested in getting non-trivial solutions. Because a trivial solution, we know that the values will be each of the components will have unknowns will be equal to 0. Isn't it? That is a trivial solution. So that is the least, at least one solution, that is a trivial solution. But in general, we would be interested in finding only non-zero solution. So it has at least one solution, namely K1 equal to 0, K2 equal to 0, etc., KR equal to 0. That is each of the constants equal to 0. We call this as a trivial solution, which I already mentioned. If this is the only solution, then S is said to be a linearly independent set. Or the vectors are linearly independent. If there are solutions in addition to the trivial solution, then S is said to be linearly dependent set. So what do you mean by that? If there are solutions in addition to the trivial solution, then S is said to be linearly dependent set. Means the vectors are linearly dependent. When the linear combination is equal to 0 such that not all Ki's are 0, then vectors are linearly dependent. That's the meaning of it. Now, let's go for an example. Determine whether the following set of vectors in R3, that means each of the vectors in R3 will have 3 components. Whether the set of vectors in R3 is linearly dependent or linearly independent or linearly dependent. S is having 3 vectors, set of all 3 vectors, V1, V2, V3, where V1 is 1, 2, 3, V2, 0, 1, 2, and V3 minus 2, 0, 1. Okay. So let us take the linear combination C1, V1 plus C2, V2 plus C3, V3 equal to 0. Linear combination is C1, V1 plus C2, V2 plus C3, V3. Now we will have it equal to 0 because we are going to solve it. So as before, C1 into 1 plus C2 into 0 plus C3 into minus 2. That is C1 minus 2, C3 equal to 0 is the first equation. Then second component, C2 into C1, C2 into, you have 2C1, second components we should take now, 2C1 plus 1C2 plus 0C3 equal to 0. And third, 3C1 plus 2C2 plus 1C3 equal to 0. So you can solve. To find out, supposing you multiply to cancel this C3, you can multiply this by 2. So you get this by 2, you get 6C1 plus 4C2 plus 2C3 equal to 0. If you add, you get C1 equal to 0. Straight away you are getting. If you add, you get, okay, 4C1, no, this is 6C1 plus 4C2 plus 2C3 0. Then if you add these two equations, minus 2C3 plus 2C3 will get cancelled. Here you will get C1 plus 6C1 plus 4C2 equals 0. Here you are having 2C1 plus C2. So if you take these two equations involving C1 and C2, again you can cancel any one of them. You can see C2 equal to 0, so that C1 will also be 0. So once the C3 is made 0, from this equation you can say C1 is 0. Once the C1 is also 0, from this equation you can say C2 equals 0. You can cross check. You can find out. So we are able to see that this linear combination giving rise to this one upon solving gives rise to the result or implies that C1 equal to C2 equal to C3 equal to 0. That is the only trivial solution. That is the only solution, and that is a trivial solution. Or in other words, the scalars are all zeros. In any linear combination of the form C1 V1 plus C2 V2 plus C3 is equal to 0 for vector C1 V2 V3, that C1 equal to C2 equal to C3 equals 0, then the vectors are linearly independent. In other words, the set having these three vectors is said to be a linearly independent vector set. Set of all linearly independent or linearly independent set. Okay. Another question. Determine whether the following set of vectors in the 2 by 2 metric space, 2 by 2 metric space is linearly independent or linearly dependent. That is, each of the vectors is here represented as a 2 by 2 matrix. Remember, vector elements can be integers, real numbers. Of course, there are complex numbers also, but according to your standard, according to your scope, we only take real numbers. And you can think of taking vectors to be represented in matrix forms also, where of course you have the entries of the matrices are real numbers. So here, each one of the vectors is represented as a 2 by 2 matrix. V1 2101, V2 3021, V3 1020. So take the combination C1 V1 plus C2 V2 plus C3 V3 equal to 0. You have to take the equation and then you find out C1 into what is V1? 2101 plus C2 plus C3. What is the right hand side then? When every vector is here is a matrix of order 2 by 2, then naturally the right hand side means here not integer 0, but a 0 matrix cap O, that is 0, 0, 0, 0. So now you know very well how to multiply a scalar with a matrix. 2C1 plus 3C2 plus C3 equal to 0. Isn't that? Then C1 plus C2 into 0 plus C3 into 0 is 0. First row, second column element. Then C1 into 0 plus C2 into 2 plus C3 into 2. That is 2C2 plus 2C3 equal to 0. Second row, first column element. And finally, C1 into 1 plus C2 into 1 plus C3 into 0. In other words, C1 plus C2 equals 0. Either you can go by elementary row operations being used in reducing this into an echelon form, and then you can go for finding the constants. Or you can easily better, I would suggest, as it is easy for you to see here, C1 equal to 0. It's very simple. Instead of going for writing augmented matrix and then taking elementary row operations and then reducing it to echelon form here. Of course, it is mandatory to get it reduced to echelon form to find the number of non-zero rows to find the rank of the matrix. If it is just finding rank of the matrix, and when it is going to be a testing of the system of linear equations to be consistent or inconsistent, you need to check whether the ranks of matrix of coefficients as well as the augmented matrix are the same. So in those cases, this is mandatory. You have to do. But here it is not necessary. It is only to find the constants C1, C2, C3, isn't it? And see that if all of them are equal to 0, then the vectors are linearly independent. Otherwise, linearly dependent. So here you can easily see C1 equal to 0. So from this equation, when C1 equal to 0, C2 equal to 0. From this equation, since C2 equal to 0, C3 is also 0. Therefore, it simply very easily gives you the result that C1 equal to C3 equal to C3 equal to 0, which means S is linearly, that is, it's a linearly independent vector set, or the vectors themselves can be called as linearly independent vectors. Before we go to, again, the rank, already, of course, we have seen, we are going to emphasize it again. In the new concept of null space and nullity, we are going to combine. This R is going to play a role to find the nullity of A. And therefore, before we take it up this, if you got any doubt in finding proving or finding the vectors to be linearly independent or linearly dependent. If you got any doubts, you can get it clarified. Is there any doubt? Hello? Anyone? Can I get any response? Hello?
Yes.
Hello? Yes, okay. Is it clear? Shall we proceed?
Yes, sir. Clear.
Okay, right. So rank and nullity. Rank already, of course, we have seen. So coming to this using independence, also we can think of the rank. But the easiest way is to reduce it to echelon form and get the number of non-zero rows to give you the rank. Okay. Now, the rank of a matrix is the maximum number of linearly independent row vectors of A. Supposing A is the matrix, its rank is also defined as maximum number of linearly independent row vectors of it. It is denoted by rank of A or R of A or small r, whatever it is. Now, the solution set of the homogeneous system Ax equal to 0. Already we have seen in the last session, solving a system of linear equations of the form Ax equal to B. Of course, we haven't gone deep into in depth to the solving, but you have just been exposed to the consistency and inconsistency having the rank of the matrix and the rank of the augment matrix. And of course, how the solution set will look like, isn't it? Ax equal to, you know very well, the system of equations 1 that we represented in the previous session. To consider the set of m equations in n unknowns, we had the matrix equation Ax equal to B. Now, if you take 0 in the right hand side, it is becoming naturally homogeneous, because if the constants are all zeros, the right hand side you have Ax equals 0. So it is a homogeneous system. So the solution set of the homogeneous system Ax equals 0, that is, suppose you have capital X, 3 unknowns x1, x2, x3, or x, y, z, or 4 unknowns x1, x2, x3, x4, isn't it? So each one will have a value, so that you have the solution set x1, x2, x3, x4 equal to -1, 2, 4, -3, something like that. So that is the solution set. So that solution set of the homogeneous system is called null space of A. Since you have the homogeneous system, that is, since you are having zeros in the right hand side, as you know very well, the homogeneous system of equations will have zeros in the right hand side, the constants. So that such a homogeneous system will group solutions, and that solution set is called null space of A, and its dimension is called the nullity of A. Everything is for the matrix, given matrix. So you have rank and nullity. Again, show that the vectors are linearly independent. A similar problem. Here, only thing that you can easily check as before. You don't need to repeat now. Same kind of one. And you can see that all the scalars are each one equal to 0, and so that they are linearly independent. So here why we have taken linearly 0, C3 equals 0, system of unique solution. And remember, for this we are going to take it up soon later, that a system is said to be consistent if rank of A and that of augmented matrix AB are the same. But when it is consistent means it has got solutions. There are two types of solutions. Another is infinitely many solutions. So when will you have unique solution? When you will have infinitely many solutions? Okay, that we are going to see soon. But still, since we have come up here, we are just going to see one thing is written here. R of A is equal to R of A 0 means here the augmented matrix, isn't it? Here 0 means actually that instead of your Ax equal to B being a homogeneous system, you have Ax equal to 0. That is cap O actually. It is matrix. A into X is product of two matrices. A is matrix of coefficients. Maybe a 2 by 2 or 3 by 3 matrix, one is square matrix. And your X is X1, X2, X3 or X1, X2, depending upon the order of the matrix. And your O is 0 matrix. Isn't it 0, 0, 0, 0 or 0, 0, 0, 0, 0, 0, 0, 0, 0, 3 by 3. Isn't it? So that's why we have either A, comma B or A, comma O actually. Isn't it? So here we are able to find, you just look at, we have found finally by elementary row operations, rank of A as well as rank of A0. Isn't it? Here AO, sorry, it's not 0, O, cap O, that is 0 matrix. Like for A, comma B, it is A, comma O. So R of A, you just look at this is a non-zero row. This is also a non-zero row. Remember, only if all the elements of the row of a row are zeros, it is called a zero row. Even if there is one non-zero element, it is called a non-zero row. Okay, so here, even though there are two zeros, it is a non-zero row. Even though there are two zeros, it is also a non-zero row. Even though there are three zeros, still it is only a non-zero row. Thus, if you just first consider this portion, that is matrix of coefficients denoted by A, by reducing into echelon form, we have got this last step. And you see that the number of non-zero rows of A is 3. So R of A is 3. And simultaneously, we are doing the elementary operations, isn't it? So we have come to the first, if you, normally for practical purpose, we just used to do a vertical line to just to make a distinction that this is A and this is O. And for any non-homogeneous system, this will be A and this will be B. So just to make a distinction, you can put a line here. So as a whole, if you look at, for the augmented matrix AO, you have non-zero row, non-zero row, non-zero row. So rank of AO is also 3. So R of A equal to R of AO equal to 3. Well, so that is okay, finding rank. So the system is consistent, okay. But here, what do we need? Question of linear independence, isn't it? So here, number of linearly independent row vectors. This is, the vectors are linearly independent. How many rows are there? That is maximum. That is the number of non-zero rows. Non-zero. So you have 3. And therefore, also they're using this basic condition that not, I mean, all the scalars are each equal to 0. We can say vectors are linearly independent. So here we are just coming to a point which is a prelude to the kind of solutions that I have just talked about, that when R of A is equal to R of AO or R of AB equal to the number of unknowns. N here stands for number of unknowns. Here, how many unknowns are there? There are 3 unknowns. Just go back. There are 3 unknowns because each vector is having 3 components. Say x1, x2, x3, y1, y2, y3, z1, z2, z3, isn't it? Therefore, there are 3 components. So, number of unknowns is, I mean, here, of course, in the linear combination, sorry, we can take it this way. In the linear combination, you have the 3 unknowns, C1, C2, C3. Okay, so you have number of unknowns. But in solving the system of equations, when you have Ax equal to B, X will be X1, X2 or X1, X2, X3 or X1, X2, X3, X4, depending upon the nature of the question, that it denotes the anyway number of unknowns that you find. Isn't it? Here unknowns are the scalar C1, C2, C3. So number of unknowns, when the ranks are equal, system is consistent. And if it is also equal to the number of unknowns, then the system is consistent and has a unique solution. And if the ranks are equal, system is consistent, but less than the number of unknowns, then the system will have infinitely many solutions. Okay, that's the additional information that we are going to see again. Show that the vectors are linearly independent and linearly dependent. So you can, here of course you have each vector 4 components. So you have 3 unknowns, C1, C2, C3, because there are only 3 vectors, but each vector has got 4 components. So you have a matrix form like this, augmented. Otherwise, you can solve by taking 2 at a time, and you can get to know that here you are able to see that again by the previous very first some T, so that you writing other vector, other constants in terms of t and substituting many values for t, like 1, you get one value. Like if you t equal to 2, another value. So it is giving you that suppose C3 equal to t and C2 equal to t and C1 is minus 2t. You have that. So the system becomes minus 2tx plus ty plus tz equals 0 because C1 is minus 2t, C2 equal to t, and C3 equal to t. So the system becomes this. That is 2x is equal to, supposing t equal to 1. The simplest value you can give. 2x is equal to y plus z. Hence the vectors are linearly dependent. That is, one vector is able to be expressed in terms of the other. Or you can even check by giving the different values that then you may ask one question. Supposing you don't go to this one, by just getting the values of 3, C1, C2, C3, you must be in a position to say whether they are linearly independent or linearly dependent. Suppose t is equal to 0, C3 equal to 0, C2 equal to 0, C1 equal to 0. Only when t equal to 0, isn't it? Suppose t is equal to here, it is any scalar, isn't it? T equal to 1, C2 is also 1, and C1 will be minus. But here, when you substitute here, you will be able to see that is very important. Okay, so only when t equal to 0, you get this is 0, this is 0, this is equal to 0. But t is not the only value you can generate. But in the previous values, you have directly found C1 equal to 0, C2 equal to 0, C3 equal to 0. So here you have gone for an assumption. Even if you are straight away solving that, you will be able to see that not all C's are zeros. Therefore, the vectors are linearly dependent. And here, as I just mentioned, you can see that R of A, when you go for reducing it to echelon form, this is your augmented matrix where you have, supposing if there is a line here, you are finding rank of A. What is rank of A? This is non-zero row, this is non-zero row, this is a 0 row, this is 0 row. Therefore, there are only 2 non-zero rows. So R of A is equal to 2. And taking all into account the augmented matrix, whose number of non-zero rows is only 2 again. So R of AO is also 2. Okay, system is consistent, but less than n because the number of unknowns is 3. So in this case, the solutions will be many because you can check that by giving various values for t, you will get various solutions. Okay. Rank and nullity. So find the rank and nullity of the matrix. First find rank. Okay, so this itself is an exercise for you being a big matrix in the sense there are 4 rows and 6 columns. Reduce by elementary row operations carefully. You have to put your hands and practice because it is not so simple to have just a 3 by 3 or 3 by 4. You have to have about 3 or 4 set of elementary row operations, set of operations. Okay, and then this is the answer. Reduced final row echelon form of A is this much. Okay, so this is your. Now, how many number of non-zero? This is only matrix A, no augmentation. Straight away, this is matrix A whose reduced row echelon form is this much. So there are only 2 non-zero rows. So rank of A is equal to 2. Okay, what is nullity? Okay. To get nullity, you need to have the formula. Remember, nullity of a matrix given is n minus r. N minus r. Okay, r is 2. Well, very simple we have found. So what is n? What is n here? Just see. So that is important. Don't jump to the conclusion to say that it is 3. We have not written any linear combination having 3 components, scalar C1, C2, C3. You are given a matrix which is of order 4 by 6. Okay, so what is the number of unknowns? That means what are the number of components a vector, each vector has. Just see that the corresponding system of equations will be. What is the corresponding system of equations? X1 is minus 1, x1 minus 4x3. So here, go to the reduced row echelon form, x1 into 1 plus 0 into x2 minus 4x3 minus 28x4 minus 37x5 plus 13x6. Each row is a vector now. Each row of the matrix can be regarded as a vector. x1 minus 4x3 minus 28 minus x4 minus 37 x5 30 x6 as a linear combination. Okay, so that is equal to 0. You are making corresponding system of equations. Similarly, the next one you have x2 0x1 plus x2 minus 2x3 minus 12x4 minus 16x5 plus 5x6 equal to 0. Thus you have corresponding system of equations only 2 in number, because the remaining 2 rows are zeros and there are 6 unknowns. So it follows that the general solution of the system is you can write x1 equal to some 4r plus 28s plus 37t minus 13u, some unknowns, giving values for x3 equal to r, x4 equal to s, x5 equal to t, x6 equal to u. We don't need to go for finding now unknowns. So we are able to find out that each vector has got non-zero vector 6 unknowns. So in general, it is n equal to 6, r equal to 2. Therefore, nullity of A is n minus r 4. Before we go deep into vector space and what are the axioms, as you have seen in your school days, what is a group? A non-empty set satisfying about 4 or 5 axioms with respect to a binary operation. In the same fashion, we can define vector space and some of its properties we can discuss. So shall we have a break for 5 minutes before we go to vector space and its properties? Shall we have a break for 5 minutes?
Yes,
Hello?
sir, sure.
Okay, fine. Shall we resume the class? Hello? Are you ready? Hello?
Yes, sir.
Okay. Just look at vector space. So here you have two binary operations. One is addition, another is scalar multiplication. A non-empty set V, because it is a set of vectors. So of elements, vectors A, B, C, etc. is called a real vector space because we are considering only real vectors. Or real linear space. Vector space can also be regarded as linear space, but most often we'll be calling it as vector space. So it's a non-empty set of vectors. And these elements, of course. If in V there are defined two algebraic operations, as I just mentioned, vector addition and scalar multiplication. That is a multiplication of a vector with a scalar. That is scalar multiplication of a vector. Vector addition as follows. Vector addition associates with every pair of vectors A and B of V a unique vector of V called the sum. That is, here it is actually talked about closure property. You know very well, to have a non-empty set to be a group G star. A star denotes any binary operation. You have closure property, associativity, existence of identity, and then existence of inverse. If further you have commutativity, you say commutative group in the same fashion, but that was only with respect to one binary operation. Here you have got two binary operations, namely vector addition and scalar multiplication of a vector. So what are the axioms to be satisfied? Commutativity. Here straight away commutativity is one of the axioms that are to be satisfied. For any two vectors A and B of V, A plus B equal to B plus A. For any three vectors A, B, C of V, you have associativity. A plus C equal to A plus B plus C. Or if you remove the brackets, it is nothing but A plus B plus C equal to A plus B. Anyway, it is A plus B plus C. There is a unique vector in V. Look at the word unique. One and only one, called the zero vector, denoted by cap O, such that for every A in V, A plus 0 equal to A. Zero vector. A vector plus zero vector equal to A. So that zero vector is your identity element. Additive identity. For every A in V, there is a unique vector in V that is denoted by minus A and is such that A plus minus A equal to 0. So 1.3 is about existence of identity element and existence of here inverse vector. Any vector added to its additive inverse. Is it right? Then it becomes 0. Zero vector. This is for, these four axioms are for vector addition. Straight away commutativity, associativity, existence of identity, and existence of inverse. Next one you have for scalar multiplication. The real numbers are called as scalars. So the scalars are the real numbers. Scalar multiplications associates with every vector A in V, every scalar C, a unique vector of V called the product of C and A, and denoted by CA or AC, such that the following axioms are satisfied. Here again you have four axioms to be satisfied for this binary operation, scalar multiplication. Distributivity. There are two distributivities. One is for two real numbers, that is scalars, you have one vector. And for two vectors, you have one real constant. So what is that? So the combination is different, that's all. Otherwise, both of them are distributivity. They get distributed. For every scalar C and vectors A and B in V, if you just have a scalar multiplication C into A plus B, you have it as CA plus CB. That is addition of vectors multiplied by C. Is C into first vector plus C into second vector. Same kind of distributivity, but this time we have two scalars, but only one vector. For all scalars C and K, and every vector A in V, you have C plus K into A equal to CA plus KA. Or C plus L, whatever be the scalar you take. So sum of the scalars into a vector is scalar into the first vector plus scalar and second scalar into the only one vector. So anyway, it gets distributed. So both of them are called distributive laws. Associativity. Here it is scalar multiplication. So for all scalars C and K and every vector A in V, it is C times Ka is the same as Ck times A. Anyway, it is CkA. Okay. For every A in V, you have this multiplicative identity. This is also identity. A into 1 equal to A plus 0 equal to A. That is additive identity. It is multiplicative identity. See, identity is nothing but the identity of the element gets preserved when you have A. When the operation is plus, it could only be above with a 0, isn't it? So A plus 0 is A. That's why it is additive identity. Whereas A into 1 is also A. So here is also identity preserved, but when it is multiplied by 1 only. Suppose you multiply by 0, you get only 0 vector. So 0 cannot be multiplied by 2, get your your identity. So 1A equal to. So when these two conditions are satisfied with respect to two binary operations of vector addition and scalar multiplication of a vector, then the non-empty set V consisting of vectors is said to be a vector space. Now, n-tuple space, Rn. So you have vector. Every vector is an ordered n-tuple. U1, U2, extra U1, one vector, say U. V1, V2, extra Vn is another vector V. What is U plus V? Addition of vectors. So you should also know the practical addition. How do we do it? What is vector addition when it comes to vectors in n-tuple space, Rn? Each vector, first components will be added up. U1 plus V1, comma, U2 plus V2, comma, etc. Un plus Vn, so that you have n components. Then scalar multiplication. K times vector U, that is U1, comma, U2, comma, U1, U2, extra U1 is KU1, KU2, KU1. That is here again, you have n tuple. Each component is the vector component multiplied by the scalar. Similarly, you can go for matrices with real numbers, say of the form 2 by 2, of order 2 by 2. So U11, U12, U21, U22 is one vector, another vector. So it is nothing but corresponding entities are to be added. U11 plus V11 is one component. That is first row, first column. U12 plus V12 is your first row, second column element. U21 plus V21 is first row, second row, first column element. U22 plus V22, second row, second column element. So again, it's again 2 by 2 matrix only. Okay, matrix addition. Then scalar multiplication. Okay, scalar K, you have a 2 by 2 matrix with the entries U11, U12, U21, U22. It's nothing but matrix having scalar multiplications as its entries K U11, K U12, K U21, K U2. So very simple. Now, to show that a set is not a vector space, you need only to find one axiom that is not satisfied. See, in mathematics parlance, the golden rule or thumb rule is that to counter any axiom or any rule, it is enough even if you prove for one result that it is not true. Similarly here, it is true always that even if for one axiom is not met, even if it is not true for one axiom, then the result is not true. So to prove that a set is not a vector space, it is enough to prove at least one axiom that is not satisfied. To take an example, the set of all integers is not a vector space. It might be true for many integers in the set of all integers for satisfying each of four axioms under a vector addition, scalar multiplication as a whole. But even if there is one axiom that is not met for any one integer, then it cannot be a vector space. So we are able to prove that the set of all integers is not a vector space. Why? 1 belongs to V. Integer. It's an element, isn't it? Half is a real number, scalar. Half is a real number, scalar. So you have the scalar multiplication, half into 1, equal to half. But it does not belong to V because V is set of all integers. So half is not an integer, isn't it? So closure property. So what is that axiom that is the axiom that is not satisfied here? Closure property is not satisfied. For A comma B belong to V, A plus B are scalar multiplication Ka must also be an element of V. So this you know very well. It is meant by, it is called a closure property. So here the closure is scalar and scalar multiplication of a vector. So k, which is C or k, half, which is a real number, and one integer, it is half multiplication, but it is not an integer. Half is not an integer, isn't it? So it doesn't belong to the set of all integers B. So set of all integers is not a vector space. Now, set of all second degree polynomial functions is not a vector space. There might be second degree polynomials where you can prove axioms, but even if there is one axiom, there is one incidence where you can prove that it is not the case, you can generalize it. For example, here you take p of x equal to x square. It's a polynomial, isn't it? So q of x minus x square plus x plus 1. And you add vector addition here. X square plus minus x square plus x plus 1. X square minus x square get cancelled, leaving behind x plus 1. X plus 1 is not a polynomial function. It's only of degree 1. It's linear, isn't it? So it doesn't belong to me because V is set of all second degree polynomial functions. Therefore, it is not a vector space. So these are also counter examples. So this, of course, already we have seen linear systems, how it looks like. This is what already I have mentioned. So anyway, we will emphasize. If the common rank R, that is common rank here, we mean the rank of A and rank of the augmented matrix AB or AX or AO, whatever it is. AO, AB or AO is less than N. Here N here stands for number of unknowns. In the solving of system of A1, 1, x1 plus A1, 2, x2 plus etc. plus A1, n, xn equal to B1, etc. etc. AM1, x1 plus etc. AMN, xn equal to Bn. So you have coefficient matrix A having entries m by n matrix is not m rows, n columns, A11, A12, etc. A1n, etc. etc. AM1, AM2, etc. AMN, and multiplied by x, the column vector x1, x2, etc. xn. And the right hand side is the constant matrix or column vector again. You have constants. So number of unknowns n. If the rank is less than n, number of unknowns, the system 1, that is, this is the system 1 we know already, isn't it? The system 1, that is system of linear equations, has infinitely many solutions. All of these solutions are obtained by determining R suitable unknowns. Okay, right. Now, anyway, okay. Now, of course, this, of course, we are going to see in detail later on. If solutions exist, they can all be obtained by the Gauss elimination. You know very well, normally we know the elimination method that we normally do by taking a pair of equations at a time and cancelling, that is eliminating one of the variables. After that, we do it in a systematic manner, and that elimination method is actually, there is a method devised by famous mathematician Gauss, and that is why it is named after him, called the Gauss elimination method. Okay, right. And of course, you can also, you may be aware of back substitution method. So whenever you have this elimination, and finally, when it is reduced to an echelon form, and then from the bottom, you are able to substitute the equations and get the other unknowns from, isn't it? Anyway, so what we are trying to say here is, if the rank of the coefficient matrix equal to rank of the augmented matrix for the system AX equal to B, which represented the linear system of equations in n unknowns, and if the rank is R, that is R of A equal to rank of A equal to rank of B equal to some same. System is consistent. That means it has solutions. It is unique if R of A equal to R of AB equal to n. Here n stands for number of unknowns. If they are equal, consistent, but less than n, then system has infinitely many solutions. That means one will be written in terms of the other. So whatever value that you give for the second one, independent variable, you get a different value for the dependent variable. So that you'll be able to generate as many solutions as possible. That's what we mean by infinitely many solutions. Homogeneous, again, you know very well, if the right hand side constants are all zeros, you have the matrix multiplication representation of the system 1 as capital A, capital X equal to capital O, where O is the zero vector. Isn't it? Okay. So this, of course, we have seen already. This has a trivial solution, x1 equal to 0, etc., xn equal to 0. Non-trivial solutions exist if and only if rank of A is less than n. If rank of A is equal to or less than n, these solutions together with x equal to 0 form a vector space of dimension n minus r, called the solution space of this homogeneous system of equations. That is called a null space of equation, set of equations. Okay. Now, again, these are all very, very simple. This might have studied in your school days. I think right from 8th standard, 9th standard nowadays, I think. So determinants. First of all, what is a determinant? Determinant is nothing but value of the matrix that can be determined. So what do we do? For the matrix, we have the row column arrangements. And they are enclosed within honorary brackets or square brackets. To determine the value of the matrix, we remove the ordinary or the square brackets, but put two parallel lines. To mean, we are going to determine the determinant of the, determine the value of the matrix, which starts from determination of or determinant of a second order matrix. Okay. So we can straight away write a determinant. Suppose A is the matrix having entries A11, A12, A21, A22. We can straight away say det A, DET capital A, means determinant of A. You don't need to write in full det A, but you read it as determinant of A. So now that don't put matrix symbol. Many of the students commit this mistake many a time, that the brackets of matrices and determinants are confused, interchanged, wrongly written. So it should be most careful about the determinant symbol, that the entries are within two parallel lines. So A11, A12, A21, A22, they are putting the symbol. Now, what is the meaning? How do you determine its value? It is called expand. It is now multiplication of the principal diagonal elements minus multiplication of the secondary diagonal elements. Here you have to be careful about it. You just don't remember like multiplication of diagonals only. So because here again, we have seen in the past, many students used to commit the mistake that they multiply this first, then they will put minus this. So remember, plus of multiplication of the principal diagonal. First element to the last element is the principal diagonal or prime diagonal, the primary diagonal. This is the secondary diagonal. So plus of this multiplication minus formula, product of these two. Okay, minus is the formula. So here you don't need to even remember plus of. Just multiply the principal diagonal elements in that order minus the secondary diagonal elements. Okay, suppose here you have some minus, then automatically this minus, that minus will become plus. So this is the formula. So this is how you expand a 2 by 2 determinant. Sometimes the determinants can also be represented by capital letter D. But this will be more applicable, more appropriate to write det of the matrix in question. Okay, det A. Right. A determinant of third order can be defined by. So D is equal to, supposing your matrix A is having entries A11, A12, A13, A21, A22, A23, A31, A32, A33, then det A or capital D is equal to, replace the matrix symbol by these two parallel lines, and you are writing the entries. Now, how do we expand? This is called the expansion of a 3 by 3 determinant. You can expand it by any one row or any one column. That is to be borne in mind. Let us uniformly say, like expand through first row. But you can check. Now, what is meant by expansion through first row? Means you first take the first row, first element. Okay. It has got a positional sign, that is plus. This has got a positional sign minus. This has got a positional sign plus, minus, plus, minus, plus, minus, plus. As far as 3 by 3 concerned, you start from plus and you go via row, then column, then row, or via column, you will get the same sign alternately. Plus, minus, plus, minus, plus. See, positional sign is different from sign attached to the number or the entry that is available there. Okay. For example, suppose you have here plus minus. Suppose here you have minus 3. Okay. You will put minus positional sign and this element minus 3. Minus of minus 3. So that you have to bear in mind. So A11 we have written here in the sense that there is a plus preceding it, which we don't need to write. Writing plus symbol is optional, isn't it? Okay, when it precedes. So multiplied by its minor. What is meant by minor of an element of a row or column of a matrix? By deleting the corresponding row and column, you are left with a 2 by 2 determinant. Is it right? A22, A23, A32, A33. Then we are expanding through the first row, isn't it? So positional sign for the second element, minus. Put the second element. Of course, here they have taken first column. Anyway, you can expand. Here this author has taken, or this example is shown like that. Anyway, you can go through the first row or say first column. Okay, here it is taken first column. So you get minus A21 multiplied by its minor. You have to be careful. Corresponding row and column is to be deleted in the sense, don't remove it from the question. Just block it. You just see that what are the elements that are available now. A12, A13, A32, A33. Just look at. Then positional sign plus. Third, first column, third element, A31 multiplied by its corresponding minor will be obtained by deleting this corresponding row and column. You get A12, A13, A22, A23. I would suggest to you all uniformly, it's better, easy, without any confusion, that you expand through the first row. Okay. Let's see some examples. Equations of a third order determinant, that is value, not equation, expansion. Expansions of a third order determinant. So this is your third order determinant, that is 3 by 3. The order of a matrix is the order of the determinant. Okay, so 3 by 3. So you let us hear how they have done. Yeah, as I suggested just now, this expansion is done through the first row. So take the first element. Remember, its positional sign is plus. I don't say don't put minus at all in the first element. Its positional sign is plus, which we know we don't need to put. Supposing here the element is -1, you need to put that value -1. That is the value of the element, value of the entry of the first row, first column. But the positional sign is plus, which is optional, which we don't need to. So here it is 1, then it's minor 6, 4, 0, 2. Minor means it's a determinant, minor 2 by 2 determinant. Okay. Then positional sign minus, the element is 3, its minor. This row and this column is to be deleted. So you have 2, 4, -1, 2, its minor. Plus last row, last element 0. Multiplied by, you know very well, by multiplying its minor by 0, you get only 0, but you should write, isn't it? 0 multiplied by its minor. 2, 6, -1, 0. Okay. So this is how we expand a 3 by 3 determinant. Now 1 into, you know how to expand a 2 by 2 determinant. 6 into 2, 12, minus 4 into 0, 0. Minus 3 into 2 into 2, 4. Look at this. Minus 4. There is minus in your formula and this product is -4, so +4. Plus 0 into This is 0. Again here minus of minus 6 plus 6. So it is 12 minus 24 plus 0. You get minus 2. Okay. So that is what it's given. This is the expansion by the first row. The expansion by the third column is, you get the minus 12. So you can do the expansion. So verify that the other 4 expansions also give value minus 2. So if you expand through any row or any column, you must get the same value. Another simple but easier, which you are already familiar with and can only be refresh and recapitulate that, as I have mentioned in the beginning, that we are going to end the session with finding solution of a system of linear equations using determinants. Using determinants is a very general term, and using Cramer's rule is a very particular term, because as it was invented by mathematician Cramer, not grammar, C-R-A-M-E-R, Cramer. His rule, so Cramer's rule. Cramer's rule for solving linear system of equations in two unknowns. Okay, you know very well what are the two equations in two unknowns. What is the general form? A11 x1 plus A12 x2 equal to B1. A21 x1 plus A22 x2 equal to B2. Okay. So what are the unknowns to be found? What do you mean by solving this system of equations? You need to find the variables values or the unknowns values x1 and x2. Isn't it? You are given A11, A12, A21, A22, the coefficient matrix A. So the unknowns are the column matrix or the vector, column vector x1, x2, x. And B is your constant matrix or column, again column vector B1, B2, which will also be known. Constants are known, coefficients are known, only no unknowns are the variables, which mean we solve the system of equations x1, x2 or xy or x1, x2, x3, xy, z, if there are three equations and three unknowns, as the case may be. So we need to find x1 value, x2 value. These are the two unknowns. So what is x1? The formula is, you have to remember that way. Formula is d1 by d. Remember, there is no division of matrices. We have addition of matrices. We have subtraction of matrices. We have multiplication of matrices. We have multiplication of a matrix by a scalar. We can do addition of rows inside, or you can multiply a row, any row inside a constant and then do the addition, subtraction. All these things are elementary row operations. Similarly, column row operations. So you can do addition, subtraction, scalar multiplication, and multiplication of the matrices, but not division. Here, by just looking at this division, don't be misled that you have division of matrices. It is not matrices. Matrix is an arrangement. It's not a simplification. It is not an expansion. It is an arrangement. It remains as it is. Entries are there as first row, first column, first row, second column, like that. But here, even if you write them in that order, it can be simplified. So as far as a system of two linear equations, the unknowns are found to be x1 equal to d1 by d. d1, these are notations only. d1 by d. Some author will say, supposing there are two unknowns x, y, they will say dx, dy, capital D suffix x, capital D suffix y. See, supposing the unknowns are x, then your x is equal to dx instead of d1, I will say d suffix x divided by d. Similarly, y is equal to dy so divided by d. So you should know what is d, what is dx, what is dy, isn't it? So d is nothing but the determinant of the matrix of coefficients, det A. What is dx then? From det A determinant, replace the first column. What is first column? Coefficients of x. Coefficients of x, first column. Replace them by constants. Keep y columns, coefficients of y as they are. Supposing 3 by 3, y and z coefficients must be kept as they are. Only the first column. This is for x. To get the dx. Similarly, keeping first and third column coefficients intact, replace the second column, that is coefficients of y, replaced by the same right hand side constants. Right hand side constants b1, b2, b3. That is dy. Z, replace the third column, that is coefficients of z, by the same. There is only one column b1, b2, b3. That is dz. So that z equal to dz by d. What is d? Originally coefficient matrix, isn't it? That is what it is here. So instead of dx, someone will say d1. And this is d2. These are just notations. So this you can expand for. Extend it to is it also if there are three unknowns. So look at this. That's what the same thing is given. X1 is actually D1. This is your D1. This is your D1. Okay, this is your D1. What is D1? Just look at what is the first column? Coefficients of X1. That is A11, A21. Replace it by the constants B1, B2. Keep the second coefficients column as they are A12, A22. This is your D1. Divided by D, of course. A11, A12, A21, A22. So what is the expansion for the numerator now? B11, A22 minus A12, B2. D. Similarly, X2 is equal to, keep the first column now as it is. A11, A21. Replace the second column, that is coefficients of X2 by B1, B2. To get X2 expansion, D. So where D is as in 1. That is we know very well. Okay, right. So what is D? So this is your D. Is it that? The most important thing is that just a minute. Power is getting so just a minute. Just Okay, now you just see that provided d not equal to 0 because since it is in the denominator, it cannot be 0. Okay. So that's very important. Now, let's consider for three equations. As I just mentioned now, just look at x1 equal to d1 by d, x2 equal to d2 by d, x3 equal to d3 by d, provided d not equal to 0. Right. So d1 can also be written as dx, dx1. If it is xy, is it dx, dy, dz, or you can simply instead of writing x1, x2, x3, it is better to write d1, d2, d3. The same way with the determinant d of the system given by 4, already we have seen. And D1 is keeping the second and third column coefficients intact, replacing only the first column because it is the coefficients of x, isn't it? Or x1 by constants b1, b2, b3. Same way, keeping the first column and the third column intact, replace only the coefficients of y, that is x2, by the same b1, b2, b3. Only one set of constants you have in the right hand side. And similarly for x3, keeping the first and second columns intact, replace the third column by the constants b1, b2, b3. So definitely you will have different values for d1, d2, d3. That's it. Note that d1, d2, d3 are obtained by replacing columns 1, 2, and 3. Columns first, second, and third, respectively, by the column of the same right hand side of this equation. Fine. That's what we understand. Okay. So Cramer's rule for two equations. It's going to be very simple. X1 equal to, of course, here they have straight away taken the determinant d1 in the numerator, d2 in the denominator. After all, their determinants can be expanded, simplified to get the number value, and the division can therefore be possible. So don't put matrix symbol, it is determinant. So what is d1? First column, you will have the constant, the coefficients of x1, 4, 2 will be replaced by 12 minus 8. And second column will remain 3, 5. Okay. Divided by D. What is D? First row 4, 3, second row 2, 5. Okay. So you expand. This is 60. You just look at here, minus formula, minus 8 into 3, minus 24. So 60 plus 24, 84. Divided by 4 into 5, 20, minus 6, 14. So 84 by 14, 6. That's that. X1 has the value 6. What is X2? D2 by D. D is the same 14, isn't it? It is going to be the same, common. And what is D2 this time? 4, 2. Remember, column wise you have to, because X is the unknown vector, which is a column vector having components X1, X2, X3. Okay, or x1, x2, x3, x4, whatever it is. So here x1, x2. So column coefficients you must consider. So to find x2, keep the first column as it is, 4, 2. Second column, 3, 5 is to be replaced by the same right hand side constants, 12 minus 18. Denominator is going to be the same, 14. So numerator now, minus 32, minus 24, minus 56. Divided by 4, minus 4. So what is the solution now? So how will we write this now? Actually, what we are supposed to write, not just writing x1 and x2. So what is that? Your question is what? Solve the following system of equations using Cramer's rule. Therefore, the solution is should write x1 equal to six. X2 is equal to minus. Now, always you can check. This is being very simple, being equation system of two equations. Anyway, supposing you are solving system of three equations, you can substitute in the left hand side of any one of the equations given the values of the unknowns that you have found, the solutions, and see that it is equal to right. That means if the equations are satisfied, even if any one of them is satisfied, of course it should satisfy all the three equations, but it is enough if you just check any one of them is satisfied, then it shows that the solution set is correct. For instance, here put x1 equal to 6, 24. 3 into minus 4, minus 12. So 24 minus 12, 12. Okay, next step. 2 into 6, 12, plus 5 into minus 4, minus 20, 20 minus 12, 12 minus 20, minus 8. So this is how you can cross-check whether your solution is correct or not. Okay. So you are given practice problems. It is for you to put your hands at trying. Practice problems, a few of them at least whenever you find time. Are the following sets of vectors linearly independent or linearly dependent? Take the linear combination equal to 0. Solve the unknowns C1, C2, C3, etc. as the case may be. If all the constants are zeros, then the set of vectors is linearly independent. Even if there is one constant that is not zero, it is linearly dependent. If it is not independent, then it's dependent. Rank by determinants. Find the rank by theorem 3, which is not very practical, of course, and check by row reduction. So it's better. So, of course, rank by determinants, but you will normally be asked to expected to find the rank only by rank. Of course, it's very easy, you can expand and you will go for minor, as we have seen in the classical definition of it. But it is, you are expected to find the rank of the matrix only by reducing it to echelon form and finding the number of non-zero rows. That is enough. Okay, that will be better. Valuation of determinants. Okay, right. For instance, you take this one. Expand this. This is a 2 by 2 determinant. Cos alpha, cos beta minus sin alpha, sin beta. Can anyone say that what it is equal to in trigonometry? Cos A, cos B minus sin A, sin B. Can anyone? Hello? There anyone to respond? Cos A, cos B minus sin A, sin B. What is it equal to? Cos of alpha plus beta, or cos of A plus B. Anyway, okay. So you can expand and evaluate. Any questions, any clarifications anyone want to seek? Anything? Anyone? Hello? Is there any feedback, any response, any questions, any clarification from anyone? Can
No,
I get
sir.
any response? Noted. Have you all understood clearly? Okay, thank you then, Shruti and others. Thank you, everyone. Okay, then I stop sharing and then end the meeting and the proceedings. Okay, thank you.
Thank you, sir.
Thank you.